There is a silence at the edge of time, a silence so vast that it swallows not only sound, but meaning. The universe, which once blazed with light and thunder, now bends slowly towards stillness. In its beginning, the cosmos was geometry in motion lines, stretching outward, arcs curving wider, a grand expansion etched into spacetime. But even geometry is mortal. Straight lines bend, arcs shatter, and the architecture of reality itself begins to unravel. Galaxies recede into the dark, their light stretched thin until it vanishes beyond perception. Stars burn down to embers, their final photons lost to the widening void. The very fabric that once carried creation forward bends toward collapse, or toward an endless freeze. What is the final shape of existence? Will the universe fold back on itself, collapsing all time and matter into a final fiery point? Will it stretch endlessly into silence, a canvas of eternal night? Or will it fracture into geometries beyond comprehension, where space itself tears apart, atom by atom, until nothing remains but broken laws? The question is more than science. It is mortality written across the cosmos. For if even the universe must die, then death is not merely the end of living things, but the destiny of space and time itself. And so the inquiry begins. What is the geometry of a dying cosmos? What shape does the end of everything take? And what does it mean to live, to breathe, to exist inside a universe that is already unraveling? The search for the universe's fate began long before modern science had words for galaxies or expansion. Ancient philosophers gazed upward and imagined eternity. To them, the sky was infinite and unchanging, the stars eternal torches set in crystal spheres. The heavens were geometry-perfected circles, arcs, and orbits repeating forever. Mortality was for men, not for the cosmos, but silence is deceptive. Beneath the sky's apparent stillness, there was motion, structure, and hidden history. The discovery that the universe itself could evolve, could grow, collapse, or die was one of the most unsettling revolutions in human thought. The story began in the early 20th century with Albert Einstein's general theory of relativity. Published in 1915, it replaced Newton's invisible pull of gravity with something deeper, the bending of space-time itself. Space was no longer a backdrop. It was dynamic, pliable, woven into the very motions of matter and light. Geometry became destiny. Matter told space-time how to curve. Curvature told matter how to move. Galaxies, stars, even the path of photons all followed the contours of this unseen architecture. For the first time, the question of the universe's overall shape could be asked in mathematical terms. Was the cosmos curved inward like a sphere, destined to collapse? Was it flat, stretching endlessly, or open like a saddle, its expansion infinite and unstoppable? Einstein himself was reluctant to imagine a universe that evolved. The equations of relativity suggested expansion or contraction, yet he desired stability. To preserve that vision, he introduced the cosmological constant, a balancing force that held the universe steady. But the geometry refused to remain still. In the 1920s, Russian mathematician Alexander Friedmann and Belgian priest-physicist Georges Lemaitre read Einstein's equations differently. They removed his balancing constant and saw what the math truly implied: a dynamic cosmos, a universe that could expand, evolve, and even die. Their solutions described a beginning, a moment of infinite density, and a possible end where geometry its self-determined fate. In a closed universe, expansion would one day reverse, collapsing into a big crunch. In an open universe, expansion would continue forever, galaxies racing apart into eternal isolation. Flatness balanced delicately between these fates. A cosmic knife edge, their ideas were bold, unsettling, and, at first, ignored. Most scientists still imagined an eternal cosmos. To speak of beginnings or endings felt almost theological, and to tie destiny to geometry seemed speculative. Yet nature had already prepared its evidence. In 1929, Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, transformed cosmology forever. By measuring the redshift of galaxies, the stretching of their light into longer wavelengths, he showed they were moving away from us, not drifting randomly, but receding in proportion to their distance. The cosmos was expanding. Space itself was stretching. The galaxies were not flying through a fixed arena. They were carried outward as the arena itself grew. This discovery vindicated Friedman and Limitor. The universe was not static. It had been smaller, denser, hotter in the past. By extension, it would not remain as it was forever. Expansion implied a beginning, and it implied an end. Suddenly, geometry became the language of mortality. The universe's curvature closed, flat, or open would dictate its destiny. The evidence deepened in the 1960s, with the accidental discovery of the cosmic microwave background. Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, detected a persistent hiss of radiation that came from every direction in the sky. At first, they suspected bird droppings in the antenna, but the signal remained. What they had found was the afterglow of the Big Bang itself, the fossil light of creation, stretched over billions of years into microwaves. It was the echo of a universe once hot and dense, now cooled and diluted by expansion. This background radiation confirmed that the cosmos had an origin, but it also suggested something about its geometry. Tiny fluctuations in the radiation's temperature hinted at the shape of spacetime itself, whether it curved inward, outward, or remained flat. With instruments like Kobe, WMAP, and Planck, humanity began to map the very geometry of the universe, pixel by pixel, photon by photon, dot. By the mid-20th century, cosmologists framed the great question in geometric terms. If the universe contained enough matter, its gravity would eventually halt expansion and curve spacetime back inward. The cosmos would end in fire, collapsing into a big crunch. If matter density was too low, expansion would continue forever. Galaxies racing apart until their stars burned out, leaving endless silence. This heat death would be the final equilibrium of entropy. Flatness represented an almost miraculous balance, a cosmos that neither collapsed nor froze, but stretched indefinitely. Its fate delicate as a knife edge. Einstein, Friedman, Limitor, Hubble, and later George Gamow theorized the relic radiation of the Big Bang formed, the lineage of thinkers who turned the universe from eternity into a story with beginning, middle, and end. The early cosmological models were not only equations but metaphors of mortality. A closed cosmos was finite life, ending in collapse. An open cosmos was exile, dispersal into loneliness. A flat cosmos was fragile balance, neither falling inward nor rushing apart too quickly. For the first time, humanity understood itself as part of a geometry that lived and died. Every star, every galaxy, every breath of life existed within a cosmic shape that carried within it the seed of its own ending. This was not the still sky of the ancients. This was not a theater of eternal circles. This was a geometry that moved, evolved, and decayed. The cosmos itself was mortal. The discovery phase was not an ending, but a threshold. With each measurement, each theory, the universe grew less eternal, more fragile, and yet the true shock was still to come. For, in the late 20th century, astronomers would look deeper into the sky and find something even stranger. An invisible force not only shaping the cosmos, but accelerating its undoing. The geometry of a dying universe was not simple. It was a puzzle written in light, in gravity, in radiation, and in the silence that stretched between the galaxies. The universe had already revealed its restlessness. Hubble had shown that galaxies were receding. The cosmic microwave background had whispered that there was a beginning. For decades, astronomers believed they had a grasp of the script. The cosmos would either collapse under its own weight or expand until it froze. Geometry seemed to be the deciding hand. A spherical universe of high density would curve inward, ending in fire. A saddle-shaped low-density universe would expand without end, fading into silence. A flat universe balanced on the edge of both. Eternally delicate, it was a grand story, but a story that still felt complete. Matter and gravity were the players. Geometry was their stage. The ending would be decided by the tally of mass across the stars. Humanity needed only to measure density, to count the visible and invisible matter, to learn whether fate was collapse or dispersal. But the universe was preparing a deeper revelation. In the closing years of the 20th century, astronomers peered at the sky with new tools, tracing the light of dying stars in galaxies far away. They expected to find the universe slowing, tugged backward by its own gravity. Instead, they discovered something that overturned centuries of cosmic intuition. The supernova that shook the sky in the 1990s. To rival teams set out to measure the rate of expansion. They used type Ia supernova stellar explosions so bright they briefly rivaled entire galaxies. Because their luminosity is consistent, these detonations could serve as standard candles, markers of distance across cosmic scales. The Supernova Cosmology Project and the High Z Supernova Search Team hunted these explosions at the edges of telescopic vision. Each supernova carried two vital pieces of information: how far away it was and how much its light had been stretched by cosmic expansion. By comparing distance and redshift, astronomers could measure the tempo of the universe's growth. The expectation was clear. If gravity ruled supreme, expansion should be slowing. Perhaps slowly, perhaps sharply, but slowing nonetheless. The universe should be like a ball thrown upward, fighting against its own weight. Yet the data said otherwise. The supernova were dimmer than expected. They were farther away than they should have been. Expansion was not slowing, it was accelerating. Birth of dark energy, this revelation in 1998 was a shock unlike any other in cosmology. The universe was not a ball thrown upward, slowing under gravity. It was a balloon inflating faster with time. Some hidden force was stretching spacetime itself. A repulsive gravity stronger than all the galaxies combined. Scientists named it dark energy, a placeholder term for ignorance, for something unseen yet inescapable. Dark, because it was invisible. Energy, because it drove expansion. The discovery overturned Einstein's equations once again. The cosmological constant, which he had once inserted to keep the universe static and later abandoned, returned as a suspect. Perhaps the vacuum of space itself contained energy, a subtle pressure that drove spacetime outward, or perhaps dark. Energy was something stranger, a dynamic field changing over time, reshaping geometry with every moment. The implication was staggering. Gravity did not dominate the cosmos. Matter was not the sole determinant of destiny. Geometry itself was not stable, but ruled by an unseen hand. Einstein's unease. Hawking's warning, the discovery reawakened Einstein's old discomfort. He had suspected that relativity permitted bizarre possibilities he could hardly accept. Expanding universes, collapsing stars, singularities where the laws of physics failed. Now his framework had revealed yet another unease space, not only curved, but stretched by something mysterious. Stephen Hawking, decades earlier, had already warned that the universe's fate might not be gentle. Black holes evaporated through quantum effects, whispering that nothing was eternal. Time itself, he argued, could have a beginning and an end. With the discovery of dark energy, his warnings took on a wider meaning. If space could accelerate apart, then the cosmos itself was fragile. The rules could shift. The stage could dissolve beneath the players. The paradigm shatters. The shock was not merely scientific, but philosophical. For centuries, humanity's intuition had leaned toward permanence. Even when stars died, the universe seemed enduring. To learn that space-time was not steady, that the geometry of the entire cosmos could unravel under a hidden force, was to see mortality on a scale far beyond imagination. The old fates, the crunch and the freeze, suddenly expanded into new terrors. Acceleration meant that galaxies would vanish beyond reach, their light stretched into invisibility. Civilizations, if they arose, would be stranded in cosmic isolation. Worse, if dark energy grew stronger with time, it could lead to a big rip, tearing galaxies, stars, planets, and atoms apart. The paradigm had collapsed. The cosmos was no longer a clockwork of matter and gravity. It was a stage haunted by a ghost, dark energy, a force that defied comprehension, dictating the end of time. The fragile balance the measurements also revealed something stranger still. The universe appeared flat, its geometry balanced on the knife edge between collapse and dispersal. Yet acceleration meant balance was an illusion. The cosmos was like a tightrope walker whose rope was being stretched beneath their feet. The numbers deepened the shock. Ordinary matter, the atoms that make stars, planets, and people, made up less than 5% of the universe. Dark matter, unseen, but gravitationally binding, comprised roughly 27%. The rest, nearly 70%, was dark energy. The very fate of geometry was ruled not by matter, but by emptiness, by something no telescope could see. The universe was not only expanding, it was expanding into ignorance. The collapse of certainty for cosmologists, the revelation was exhilarating and terrifying. The universe had defied their predictions. The neat dichotomy of crunch versus freeze dissolved into chaos. New possibilities emerged: eternal acceleration, catastrophic rips, vacuum decay. Each was stranger than the last, and each carried consequences that rewrote reality. The scientific shock was more than numbers on a graph. It was a collapse of certainty. For if geometry itself could betray expectation, then the laws that seemed so solid could falter. The universe was not the eternal stage of Newton's heavens. It was not the balanced machine of Einstein's correction. It was a dynamic, unstable structure, ruled by forces beyond comprehension. The cosmos had revealed its mortality in a new and terrifying way. Its geometry was not fixed, but fragile, not eternal, but destined to die in forms yet unknown. The scientific shock did not end with the discovery of dark energy. It deepened with every measurement, every satellite, every simulation that confirmed its presence. The universe was not what it seemed. Its destiny was no longer predictable by the simple count of matter. A hidden hand was shaping the geometry of death. The next step was inevitable. If acceleration was real, then scientists needed to probe deeper. They needed to measure the curvature of spacetime with precision, to listen for the whispers of cosmic fate. The geometry of the cosmos was a puzzle more profound than ever imagined, and the tools to explore it were just beginning to awaken. The shock of dark energy left the cosmos transformed. The universe was not slowing in its expansion, but racing outward faster than before. If true, then destiny itself had changed. But science does not stop at revelation. It digs deeper, demanding proof, detail, precision. The question of geometry, the question of fate, could no longer be left to theory. It had to be measured, mapped, confirmed across the heavens. Astronomers set out to probe the shape of space-time itself, searching for the silent language that dictated the end of everything. The discovery of acceleration rested on the faint light of distant supernova. These exploding stars, scattered across billions of light years, became signposts. With each observation, astronomers refined the curve of expansion. Dozens, then hundreds, of supernova were catalogued. Their light revealed that not only was acceleration real, it had begun several billion years ago. For nearly half the universe's lifetime, gravity had slowed expansion. But then, dark energy had taken hold, overwhelming gravity's pull, pushing galaxies apart with increasing speed. This transition was more than data points. It was history written in light, a cosmic biography where the balance of forces shifted. The universe had once been governed by attraction. Now it was governed by repulsion. Its very geometry had changed course midstream. To understand geometry fully, scientists turned to the oldest light of all, the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the afterglow of the Big Bang with unprecedented precision. Tiny fluctuations in temperature across the microwave sky carried the imprint of geometry. If the universe was closed, light would bend inward, patterns would appear smaller. If it was open, patterns would stretch larger. In a flat cosmos, the angles would remain true. After years of mapping, WMAP delivered its verdict. The universe was astonishingly flat, with a margin of error of less than 1%. This result was profound. Flatness suggested an infinite stretch, a geometry balanced on a razor's edge. But acceleration complicated the picture. Flatness did not mean stability. It meant the universe was poised, delicately, under the sway of dark energy. A stage stretched tight, but trembling with instability. In 2009, the European Space Agency launched Planck, a satellite designed to take the next step. With higher sensitivity and resolution, it mapped the microwave background with exquisite detail, capturing temperature variations 1 part in a million. Planck confirmed the flatness, but also deepened the mystery. The data revealed slight anomalies, cold spots, and asymmetries that hinted at physics beyond the known. Some speculated these scars might be the fingerprints of other universes, collisions in a multiversal sea. Others argued they were statistical flukes, yet the broader message was clear. The cosmos was flat, accelerating, and dominated by dark energy. Its geometry was neither eternal nor self-contained. Another tool emerged from the large-scale structure of the universe itself. In the early cosmos, sound waves rippled through hot plasma, compressing matter into subtle patterns. These ripples, known as baryon acoustic oscillations, left their imprint on the distribution of galaxies by mapping galaxies across billions of light-years. Surveys like the Sloan Digital Sky survey traced these frozen sound waves. They served as rulers of cosmic geometry, independent checks on flatness and expansion. The results echoed what supernova and microwaves had said. The universe was accelerating, its geometry stretched by dark energy. The convergence of evidence left little doubt, but as measurements sharpened, another revelation emerged. Acceleration meant that galaxies were vanishing not physically, but observationally. Beyond a certain horizon, light could never reach. Us, carried away faster than it could arrive. Every year, more galaxies crossed this invisible boundary. In the far future, only the closest cluster would remain visible. The universe was not only expanding, it was isolating. Cosmic neighborhoods were becoming islands, cut off forever. This horizon was a new kind of geometry, not curves of space, but boundaries of knowledge. What lay beyond could never be observed, never measured. The universe was both infinite in scope and finite in accessibility. It was geometry, not just of structure, but of silence. While satellites mapped the universe, black holes provided a microcosm of its destiny. Within their event horizons, spacetime curved so steeply that escape became impossible. They were collapses of geometry, singularities where equations broke down. In them, scientists saw an echo of cosmic fate. If the universe could collapse into a singularity at its ender, Big Crunch, it would mirror the geometry of black holes. If instead it stretched outward into silence, it would echo Hawking's vision of black holes evaporating, whispering away their energy into emptiness. In this way, black holes were both laboratories and metaphors. They revealed that geometry could fail, that space-time could fracture, that endings were not only possible but inevitable. Yet the deeper the investigations went, the more contradictions appeared. The universe was flat, yet accelerating. Gravity-bound galaxies, yet dark energy tore them apart. Locally, geometry collapsed into black holes, while globally it stretched into infinity. How could collapse and expansion coexist? How could the same laws that created stability also predict dissolution? The contradictions revealed something profound. Geometry was not a fixed stage. It was a dynamic player, a fragile construct shaped by matter, energy, and forces still unknown. To probe deeper was not only to map the cosmos, but to confront the possibility that our equations were incomplete. By the early 21st century, humanity's tools had drawn a map of the cosmic stage. Supernova traced acceleration, WMAP and Planck mapped flatness, galaxy surveys measured ripples of sound, black holes revealed collapse in miniature together. They told a single story. The cosmos was fragile, unstable, and mortal. Its geometry was not fixed, but guided by forces that defied comprehension. The investigation had revealed more than answers. It had revealed deeper layers of mystery. If dark energy dominated, what was it? If geometry was flat, why? If galaxies were vanishing beyond horizons, what remained unseen? Every measurement expanded knowledge, and every expansion deepened the unknown. The deeper investigation was both triumph and unease. Humanity had mapped the shape of the cosmos, traced its expansion, glimpsed its destiny. But in doing so, it uncovered contradictions and mysteries that only sharpened the terror of impermanence. Geometry was no longer the serene language of circles and arcs. It was the fragile outline of a universe that was already unraveling. The universe had spoken. Its geometry was flat, its expansion accelerating, its destiny written in forces unseen. Yet every revelation was only the opening of a deeper abyss. What science had uncovered was not certainty, but escalation possibilities, darker, stranger, and more terrifying than any myth. The cosmos was no longer a serene stage of stars. It had become a fragile structure, trembling between extremes, its end hidden in riddles. Each new model of cosmic death carried with it not only mathematics, but dread, for every geometry of ending was more haunting than the last. The most ancient vision of ending was entropy, the slow grinding down of order into disorder. Heat death is the geometry of exhaustion. In this model, expansion continues forever. Stars burn out, one by one. White dwarfs cool into black husks. Neutron stars fade, their radio pulses silenced. Even black holes, the last anchors of structure, evaporate through Hawking radiation, whispering away their mass into faint streams of particles. In this scenario, the geometry of the universe stretches endlessly into flatness. Space expands, but with nothing left to fill it. The last light redshifts into invisibility, photons stretched until they no longer carry energy. The cosmos becomes a canvas of silence, featureless, eternal, absolute. It is a terrifying vision, not because of violence, but because of stillness. Heat death is not fire or collapse. It is forgetting. It is the infinite dispersal of everything into nothing. But acceleration is not guaranteed to last. If dark energy is not constant, if it weakens or reverses, the universe may yet fall back. Gravity could reclaim dominance, turning expansion into contraction. In this model, galaxies halt in their retreat. The cosmic fabric bends inward. Distances shrink, collisions multiply. The night sky fills with fire as galaxies crash together. Eventually, the entire cosmos collapses into a single pointer, singularity of unimaginable density and heat. The Big Crunch is the geometry of return. It mirrors the beginning, the fireball of the Big Bang, but in reverse. Time itself would fold inward, space collapsing into a final point where equations break. To contemplate the crunch is to confront mortality in its most violent form, not dispersal, but implosion, a universe consumed by its own weight. Yet perhaps the most terrifying possibility is not stillness or collapse, but dismemberment. If dark energy grows stronger with time, its repulsion could overwhelm all forces, even at the smallest scales. In the geometry of the Big Rip, galaxies first tear away from one another. Then stars are ripped from galaxies, planets from stars, atoms from planets. Finally, even the bonds of nuclei snap, torn apart by the accelerating expansion of space itself. This is not collapse into fire, nor fading into silence. It is disintegration of reality. Spacetime itself fractures. The very framework of existence ceases to hold. The rip is terrifying because it spares nothing, not even the smallest structure. It is geometry not unraveling gently, but shattering, piece by piece, until all that remains is fragmentation. There is yet another vision, one born not of expansion, but of quantum instability. The laws of physics may not be final. Our universe may exist in a false vacuum, a temporary state of energy that could collapse at any moment into a lower, more stable form. If this happens, a bubble of true vacuum would form and expand at the speed of light. Within its boundaries, the laws of physics would be rewritten, particles, forces, even spacetime itself altered. No warning, no resistance. Reality would be replaced in an instant. This ending is geometry undone at its foundations. It is not expansion or collapse, but replacement or cosmos, overwritten by a different one. With no trace of the old. Vacuum decay is terrifying because it is silent. It carries no signs, no approach. At any moment, the bubble could arrive, and everything would vanish into laws that cannot be imagined. Each of these endings, heat, death, crunch, rip, decay, draws its power not only from physics, but from the terror of time. The universe is not eternal, it is mortal. Its geometry is fragile, contingent, temporary. The most haunting truth is that time itself may collapse with geometry. For if space-time is the fabric of causality, then its death is not only the end of matter, but the end of before and after. Death not just of things, but of meaning. In the big crunch, time implodes. In heat death, time stretches into infinite monotony. In the big rip, time fractures as events are torn apart. In vacuum decay, time is simply erased. The escalation is not only scientific, but existential. The universe is not a stage outside time, eternal and unchanging. It is time itself, and time is dying. To explore these endings, scientists turn to supercomputers, billions of galaxies, trillions of particles, simulated across cosmic scales. These models stretch the future forward, tracing the acceleration, the clustering, the dispersal. The results are chilling. In simulations of heat death, galaxies drift apart until each is alone. In big crunch scenarios, cosmic web filaments collapse, pulling all matter into fire. In big rip models, the scale factor of the universe diverges to infinity in finite timer, countdown to dismemberment. In vacuum decay, quantum fields collapse, creating expanding bubbles of annihilation. These simulations are not prophecies. They are possibilities, but each possibility carries a geometry of doom. And yet, even as these fates multiply, mystery deepens. For no one knows what dark energy truly is. No one knows if it is constant, dynamic, or illusory. No one knows if vacuum decay is possible or merely speculative. The escalation of endings is an escalation of ignorance. The more we learn, the more fragile our knowledge becomes. Every model is haunted by uncertainty, every prediction shadowed by unknowns. This is the paradox. The closer we come to understanding the universe, the clearer its mortality becomes, and the less certain we are of its end. What began as the simple measurement of galaxies has escalated into the recognition that the universe is not secure. Its geometry is temporary. Its stage is fragile. Its endings are multiple, strange, and terrifying. The cosmos may freeze. It may burn. It may rip apart. It may be rewritten by a bubble from beyond. Each is more terrifying than the last, and each is possible. The mystery has deepened to its core. Geometry is not merely the shape of space, it is the fate of existence. And the universe, vast though it is, carries within it the seeds of its own unraveling. The deeper science ventured into the geometry of the cosmos, the more it encountered endings that felt less like predictions and more like riddles. Heat death, big crunch, big rip, vacuum, decayage, was not only a possible fate, but a mirror reflecting the fragility of the universe itself. To resolve the uncertainty, physicists turned not only to observation, but to theory. The language of relativity, of quantum mechanics, of speculation stretched to its edge. It was here, in theory, that geometry became something more than shape. It became destiny. The framework for cosmic geometry began with Albert Einstein. In 1915, he unveiled general relativity, the vision of gravity not as a force, but as the curvature of spacetime. Mass and energy bend geometry. Geometry dictates motion. Applied to the universe as a whole, relativity predicts that cosmic destiny depends on density. Too much matter, and space curves inward, leading to collapse. Too little, and expansion continues. Forever. Balanced perfectly, the universe would hover on the edge of infinite flatness. For decades, cosmologists clung to this trinity. Closed, flat, open. The possible fates crunch, equilibrium, dispersal, were embedded in Einstein's equations. Yet relativity alone could not explain acceleration. For that, something new was needed. In the late 1990s, supernova observations revealed acceleration. To explain it, cosmologists resurrected Einstein's abandoned cosmological constant, a term representing energy of empty space. This constant could act as a repulsive force, stretching geometry apart. If it was truly constant, the universe would end in heat death, an endless freeze as expansion outran gravity. But speculation stretched further. What if dark energy was not constant, but dynamic? What if it was a field that changed over time, growing stronger or weaker, shaping endings far stranger than equilibrium? This possibility gave rise to the idea of quintessential rolling field of energy, whose behavior could dictate whether the universe freezes, crunches, or rips apart. Unlike a constant, quintessence could evolve, turning cosmic fate into something fluid, contingent, unstable. Parallel to relativity was another law, older and more universal, the second law of thermodynamics. Entropy, the measure of disorder, always increases. Systems tend toward equilibrium, toward heat death, applied to the universe. Entropy suggests that even without dark energy, all processes eventually grind down. Stars burn out. Energy spreads evenly. Structure dissolves. The heat death model is thus not only geometric, but thermodynamic. The universe expands into flatness, while entropy expands into uniformity. Geometry and disorder march together toward silence. But thermodynamics also opens speculation. If entropy always increases, what does that mean for time? Some theorists propose that the arrow of time is bound to entropy, and if entropy ever reverses in a big crunch, time itself might run backward. Geometry would not only collapse, causality itself could invert. Relativity and thermodynamics painted bleak fates, but quantum theory suggested another possibility. At the smallest scales, space and time are not smooth, but granular, stitched. From quantum threads, loop quantum cosmology proposed that these quantum geometries could prevent singularities. Instead of collapsing into an infinite point, a crunch might rebound, creating a new expansion, a cosmic bounce. In this vision, universes die, but their deaths seed new births. Each cycle carries echoes of the last, a geometry of renewal rather than annihilation. Speculative though it is, the bounce offers a vision of hope. Death would not be silence, but transition. The end of one cosmos could be the beginning of another. Another speculation emerged from black hole physics. Stephen Hawking proposed that black holes radiate away their energy, evaporating over time. Yet this led to a paradox. Did information vanish with them, violating quantum law? Physicists responded with the holographic principle, the idea that information is not lost, but encoded on surfaces, like a hologram. Reality itself might be a projection, geometry an illusion emerging from deeper information, applied to the cosmos. This principle suggested that even in death-heat death, crunch, or rip information might survive. The geometry of space might dissolve, but the record of existence could remain, etched on horizons we cannot yet see. It was speculation, but profound. It suggested that cosmic death was not annihilation, but transformation geometry giving way to information. As cosmologists pushed deeper, they encountered speculation on the grandest scale, the multiverse. In the model of eternal inflation, our universe is only one bubble among countless others, each with its own geometry, its own laws, its own fate. Some universes collapse quickly, others expand eternally. Some may rip, some may freeze, some may bounce into renewal. The anomalies in the cosmic microwave background, the strange cold spots, the asymmetries were sometimes interpreted as scars of collisions with other universes. If true, our cosmos is not an isolated stage, but one among infinite geometries. Its death would not be absolute, but one transition in an endless sea. Among the most unsettling speculations was vacuum decay. The Higgs field, discovered at CERN in 2012, determines the masses of particles. Calculations suggested it might sit in a metastable stator, false vacuum. If true, the universe could collapse into a lower energy state. A bubble of true vacuum would form, expanding at light speed. Rewriting physics, this was not only geometric death, but ontological. The very laws of reality would be erased, replaced by laws we cannot imagine. The possibility remains unproven, but its implications haunt physics, for it means the universe is not only temporary in shape, but temporary in essence. String theory, the attempt to unify relativity and quantum mechanics, offered yet more speculative visions. In its higher dimensional landscapes, our universe is a brain-one membrane among many, floating in a higher space. Collisions between brains could create big bangs. Separations could dictate cosmic death. Geometry is not self-contained, but part of a larger structure. In this vision, death is not final. Universes may collide, fragment, or give birth endlessly. Geometry is not absolute, but relational, shaped by dimensions we cannot see. Each theory dark energy, entropy, quantum gravity, holography, multiverse, brains paints a different ending. Some are bleak, some are strange, some are hopeful. What unites them is uncertainty. The universe is vast, but our knowledge is fragile. Every speculation reveals not certainty, but possibility. Every geometry of death is a mirror of ignorance. And yet, speculation is not futility. It is exploration. By imagining endings, physicists test the limits of law, the boundaries of comprehension. In doing so, they glimpse not only fate, but truth. The cosmos is temporary, its geometry fragile, its death inevitable in some form. For science, speculation is not indulgence, but necessity. To confront the geometry of a dying cosmos is to confront questions that may never be answered. But in the asking lies meaning. Each theory is a meditation on impermanence. Each model is a reflection of mortality. For in the death of the cosmos, humanity sees its own reflection, fragile beings in a fragile universe, wondering not only how it ends, but why it exists at all. To stare into the fate of the universe is not an act of philosophy alone. It is also the work of instruments, mirrors of glass, detectors of light, chambers of particles, and satellites peering across the abyss. For the geometry of a dying cosmos is not written only in thought, but in data. Humanity, fragile as it is, has begun to measure the end. And so, across mountains, deserts, oceans, and the vacuum of space, machines have been raised like monuments, each one an eye upon eternity. The revelation of acceleration was born not in theory but in observation. Type Ia supernova exploding stars of consistent brightness served as cosmic candles. By comparing their known luminosity with their apparent faintness, astronomers gauged distance in the 1990s. To teams the Supernova Cosmology Project and the High Z Supernova, search tracked dozens of these explosions across billions of light-years. The results were shocking. Instead of slowing, the expansion was quickening. The geometry of space was accelerating outward, as though driven by a hidden hand. Even now, supernova remain the frontline tools of cosmic measurement. Each flare of light is a clock, a ruler, a whisper of geometry. But to probe geometry in detail required more than distant candles. It required the fossil glow of the Big Bang itself, the cosmic microwave background. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, mapped this radiation with unprecedented precision. It revealed a universe astonishingly flat, balanced to within fractions of a percent. A decade later, the European Space Agency's Planck satellite refined the map. Its measurements etched the cosmic blueprint: density, curvature, expansion history. With Planck, humanity could say with confidence that space is flat, that dark energy dominates, that geometry itself is dictated by the unseen. Yet Planck also revealed anomalies, cold spots, asymmetries that hint at deeper mysteries. Perhaps scars of inflation, perhaps signs of other universes brushing against ours. The geometry may be flat, but its story is not simple. Another tool lies in the clustering of galaxies. In the early universe, pressure waves rippled through plasma, creating patterns of density. When the cosmos cooled, these waves froze into structure, leaving faint imprints known as baryon acoustic oscillations. By measuring these patterns in the distribution of galaxies, astronomers gain another ruler, another way to trace cosmic expansion. Surveys like the Sloan Digital Sky Survey and the Dark Energy Survey chart the vast web of galaxies, their clustering revealing how geometry evolves over billions of years. It is the music of the early universe, frozen into the shape of the cosmos, now serving as a guide to its fate, while large-scale geometry is traced in galaxies and supernova. Black holes provide laboratories of collapse. They are microcosms of cosmic death regions, where geometry caves in on itself. X-ray telescopes, like NASA's Chandra Observatory, peer into accretion disks, measuring matter as it spirals toward oblivion. Radio arrays, like the Event Horizon telescope, capture silhouettes of shadows. The first images of spacetime curved into silence. These instruments probe the boundary between relativity and quantum mechanics, where information, energy, and geometry collide. They are windows into the same questions that haunt cosmic destiny. Does geometry collapse, or does it transform? Launched in 2021, the James Webb Space Telescope became a time machine, peering farther than any before. Its infrared eyes capture galaxies born only hundreds of millions of years after the Big Bang, probing the dawn of expansion. By studying the earliest structures, Webb informs the fate of the cosmos. How quickly did galaxies form? How did dark matter sculpt them? How has dark energy shaped the arcs of time since then? Each faint galaxy Webb reveals is not only a window to the past, but a constraint on the future. Geometry is measured not only at its end, but at its birth. But Webb is not alone. In 2023, the European Space Agency launched Euclid, a mission dedicated to mapping the dark universe. Its task, to chart billions of galaxies across space and time, measuring how dark energy sculpts geometry. Soon it will be joined by NASA's Nancy Grace Roman Space Telescope, designed with the same purpose to trace the fingerprints of dark energy with unparalleled precision. These instruments are not merely telescopes. They are cosmic surveyors, measuring the very fabric of spacetime. Their goal is audacious: to determine whether dark energy is constant, dynamic, or something stranger still. For in that answer lies the fate of all geometry. Another revolution arrived in 2015, when LIGO detected ripples in space-time gravitational waves from merging black holes. Suddenly, humanity could listen to geometry itself. Each chirp of detection reveals not light, but motion, space-time ringing like a cosmic bell. These waves confirm relativity, but also hint at the unknown. Future detectors, like LISA, the Laser Interferometer Space Antenna, to be launched in the 2030s, will listen across the cosmos, sensitive to mergers of supermassive black holes, to the faint background hum of the early universe itself. If space can sing of its beginning, perhaps it can also sing of its end. Not all tools stare into the sky. Some probe the smallest scales. Particle accelerators, like CERN's Large Hadron Collider, test the Higgs field, the same field whose stability determines whether vacuum decay is possible, by measuring couplings, masses, and quantum behaviors. Physicists attempt to decide whether the universe sits in true stability or in a false vacuum, poised for collapse. Here, geometry is not only cosmic, it is quantum, embedded in fields and particles that weave the fabric of space. The fate of the universe may hinge on numbers measured in laboratories deep beneath the Earth. Alongside telescopes and accelerators are simulations, digital universes evolving across billions of years. Supercomputers like those of the and Millennium simulations model galaxies, dark matter, dark energy, and the growth of structure. They project futures, some of freezing emptiness, some of collapsing fire, some of rending apart. Each simulation is a rehearsal of endings, a theater where geometry's fate plays out in equations. Though no simulation is final, each sharpens the boundary of possibility, bringing the geometry of death into sharper focus. Yet despite all tools, satellites, telescopes, waves, colliders, the question remains unresolved. The fate of the universe hangs on unknowns. The true nature of dark energy, the stability of quantum fields, the possibility of higher dimensions. Science advances, but the mystery persists. Geometry refuses to reveal its final shape. Perhaps the end is millions of trillions of years away, hidden beyond any measurement. Or perhaps it is closer, written already in instability. Humanity's instruments may never know for certain, but the pursuit itself carries meaning. To build machines that measure the sky is to reach across time, to place fragile hands against the walls of eternity. The tools are vast, the measurements cosmic, yet behind them are human beings, astronomers in mountaintop domes, engineers guiding satellites across the void, physicists watching faint signals of waves ripple through detectors. The geometry of a dying cosmos is not only traced by instruments, it is traced by minds that dare to ask, by hearts that confront the silence. Humanity is fragile, yet it has raised machines that measure the depth of universes. That act alone is profound. To know that the cosmos will end, and yet to measure it, is to stand at the edge of eternity and still persist. The universe is vast beyond comprehension, older than stars, wider than imagination, and yet its fate is not exempt from impermanence. Geometry, the quiet scaffold of existence, will one day fail. The question is not whether the cosmos will die, but how. And in the contemplation of its death lies a mirror, a reflection of human fragility, of time's brevity, of the finite nature of all things. At the dawn of time, the cosmos blazed with light. Galaxies bloomed like flowers in the void. Stars forged the elements of life, and space itself swelled outward in a grand expansion. Yet even at its birth, death was woven in. Expansion could not be eternal in its innocence. Entropy crept forward, dark energy stirred, and geometry bent toward silence. Now, as science measures with precision, we see the trajectory laid bare. Galaxies drifting beyond reach, light redshifting into invisibility, heat dispersing into uniform cold. The silence after creation is not an ending that comes suddenly, but a slow fading, an unraveling written across trillions of years. To imagine this silence is to imagine a cosmos without witness, a place where stars no longer shine, where atoms no longer bind, where space itself stretches beyond form. This silence is terrifying, and yet profoundly beautiful, for it means that creation was fragile, fleeting, and luminous precisely because it had an end. Human beings are mortal. Lives last only decades, civilizations only centuries, species only millennia. To contemplate the death of the universe, then, is to expand mortality to the largest scale. Stars live and die, galaxies form and collapse. Even space-time is temporary. The mortality of the cosmos reveals that impermanence is not an accident of life, but a law of existence itself. This recognition binds the human and the cosmic. Just as the universe is finite, so too are lives. Just as galaxies fade, so too do civilizations. And yet, just as galaxies leave behind light, humans leave behind memory, knowledge, meaning. Mortality does not erase significance. It deepens it. There is a paradox in this story. The universe may fade into silence, but within its brief window of light, it produced consciousness, fragile minds capable of asking why. In the span of mere centuries, humans have gone from seeing stars as eternal fires to measuring the curvature of the cosmos. They have built telescopes that look to the beginning of time, detectors that listen to the trembling of spacetime, equations that predict the death of reality. That such beings exist at all, in such a fleeting moment of cosmic history, is extraordinary. The paradox is this: though the cosmos will end, it has given rise to awareness that can contemplate endings. The geometry of death gave birth to minds capable of reflection. Every theory of cosmic fate, heat, death, crunch, rip, vacuum, decay feels like an ending. Yet endings are rarely absolute. A star's death, seeds, planets, a galaxy's collision spawns new forms. Even black holes, in their silence, radiate faint whispers of hawking light. So too, perhaps, with the cosmos itself. A big crunch may rebound in a bounce. Heat death may dissolve into quantum fluctuations that spark new birth. Vacuum decay may not only destroy, but also create, birthing a universe with new laws. This speculation does not soften the terror of endings, but reframes them. Endings are not always annihilation, they can be transformation. Death is not absence. It is change. Underlying this reflection is an unsettling truth. The laws of physics themselves may not be eternal. Dark energy accelerates expansion. The Higgs field may be unstable. Constants may drift. Geometry may collapse not only in space, but in law. For humanity, this fragility is humbling. The universe is not a fortress of permanence. It is a temporary arrangement, contingent, vulnerable. Its laws are scaffolding, not absolutes. And yet, in this fragility, there is wonder. To live in a universe with unstable laws is to live in a universe capable of change. Without fragility, there would be no stars, no planets, no life. The geometry of impermanence is also the geometry of possibility. In the dying cosmos, humanity sees itself fragile, brief, luminous. Just as galaxies will fade, so too will civilizations. Just as entropy spreads, so too does memory dissolve. But within that fragility lies meaning. The cosmos may not last, but within its span it gave rise to consciousness that can love, create, dream. The mortality of the cosmos is not a void. It is a canvas upon which significance is painted. To understand the death of the universe is to understand life itself. Both are finite. Both are precious. Theories predict endings, but they do not close the question. Science has revealed possibilities, not certainties. Perhaps the cosmos will freeze. Perhaps it will collapse. Perhaps it will tear itself apart. Or perhaps there is something beyond comprehension, an ending no equation can capture. In this uncertainty lies hope, for it means the story is not finished. The geometry of death is not yet written. Humanity, in its brief moment, stands in the middle of a mystery, and mysteries are not despair. They are invitations to wonder. In the end, the geometry of a dying cosmos is not only about physics, it is about perspective. To see the universe fade is to see impermanence at every scale. To measure its curvature is to measure mortality. To imagine its silence is to imagine the fragility of existence itself. And yet, that fragility is profound. The universe is not eternal, but within its span, it has produced galaxies, stars, life, and thought. Geometry may end, but meaning has already been born. Perhaps this is the final geometry, not the shape of space, but the shape of awareness. A cosmos that dies, but in dying, produces reflection. A universe that ends, but in ending, teaches impermanence. Picture the last moments. Galaxies drift into invisibility. Stars extinguish into black dwarfs. Black holes evaporate into whispers of radiation. Geometry stretches into silence. In that silence, nothing moves, nothing shines, nothing remains. And yet, even then, the memory of a cosmos that once was persists in physics, in speculation, in consciousness that dared to wonder. The geometry of a dying cosmos is therefore not tragedy alone. It is revelation. It tells us that impermanence is universal, that endings are inevitable, that fragility is the essence of existence. And perhaps that is enough, for to live, to think, to reflect, within the brief light before silence that is meaning itself.